quickly just review a little bit of the group theory that I'm doing, because I'm setting up to set up the non-abelian case, Yang-Mills theory. And so basically what I was doing is I was doing SU2. I took two objects, psi is, upper psi 1 and psi 2, and I took the invariance, psi prime is u psi, where this is then a 2 by 2 matrix. And if you factor out a phase, so it's a unitary matrix, if you factor out a phase, it's written u is e to the I alpha dot tau, where these are the Pauli matrices. Okay. And we then wrote invariants, things like psi bar psi are invariant. But even more interesting are things like psi bar tau dot pi, where that's some set of vector field psi, is invariant if you take tau dot pi prime, the transformed fields, to be u tau dot pi, u dagger, which you can take the trace on both sides. So if I take trace tau I tau dot pi prime and work that out, so you take the trace on the other side too, that ends up telling us that pi prime I is some Rij, pi j, and you can work out what Rij is if you want. Rij is 1/2 trace tau I u tau j u dagger. Okay. So let's see invariances in SU2. The nice thing about this set of notation is that it generalizes. So if I now want to do SUN, okay, everything just basically stays the same. I take psi is psi 1, psi 2, down to psi n component guy. I take u, so the invariance is psi goes to u psi again. Where this is now a unitary n by n matrix. Okay. If we factor out an overall phase again, so you can always factor out that overall phase, then you can always write a unitary matrix as e to the I Hermitian matrix. So if I write the Hermitian matrix as I times the overall phase, so there's the overall phase times that's the unit matrix, and then there'll be some other stuff where these are n by n Hermitian, matrices. Okay, so now we have these new matrices called lambda, which are n by n Hermitian, and if you have, so lambda I are n by n Hermitian matrices, and by definition, since I pulled out the overall phase, these guys can be taken to be traceless. Okay, the trace is the overall phase. We got in by information matrices. If you do the counting, there's n squared minus one of them. So there's n squared Hermitian matrices, and then the trace removes one of them. So I then runs 1 up to n squared minus 1. And there's not too much that you need to know about it. Here's the only two things that we end up using. In fact, I think we use this one. So trace, we can choose them lambda I, lambda j is 2 delta ij. This is just a convention. We just pick them to be orthogonal by and normalize them that way. So that's a convention. There's nothing deep about that. And the other thing that we use is lambda I commuted with lambda j is 2i fijk lambda k. Okay, and that, so there's some matrices fijk which are antisymmetric, but for our purposes we don't really need to know what they are. But this follows actually from the fact that these are Hermitian. So this side here then, the anticommutator of two Hermitian matrices is anti-Hermitian. It's also traceless. Okay, so it's anti-Hermitian because it's a commutator. It's traceless because if I take the traces out, it vanishes. So it has to be expandable in terms of her Hermitian traceless well, if you pull out a factor of I, Hermitian traceless matrices with some coefficient, and so that's the definition of it. Okay, so not a lot of work goes into that. It's not a deep property. And given some basis, you can calculate it, but we don't really need to know it. Okay. Okay, so there's the setup. So here again, you can do invariance. Anyone want to ask questions about that, since I'm not doing too much more on SUN than that? Yes. So, thought you might.
So the commutator of two remission or anti-remission, right?
Yeah. So let's take. Yeah. So if you take lambda I, lambda j, and I take the dagger of that, the Hermitian conjugate of that. So that's the first term is lambda j dagger, because you reverse the order when you take it, lambda I minus, there's a dagger there too, lambda I, lambda j dagger, and those are Hermitian, so it's an anti-Hermitian. Okay, and that's then enough to get this property. Because if I pull out a factor of I, this has to be Hermitian and traceless, and therefore it has to be expandable in terms of these matrices. And if you give me a basis, I can read out the numbers. Okay, and if you look up in SU3, those numbers are known, but you can do you never really need to know them. I mean, there are various tricks when you do explicit amplitudes. You sum over them, but for example, I have no idea what they are in SU4, SU5, or anything like that. It's not something you need to know. And I only know them in SU3 because I've done a lot of SU3 work. But you can live without them. And good group theorists would live without them. Okay, so we want to do invariance again. Well, it's the same game. So psi dagger psi is an invariant, or psi bar psi is an invariant. And you can also have interactions with a set of fields. So let's define some vector fields, VI, so vector under this group. So this I here runs over the same indices as the lambda matrices. I is equal to 1 up to n squared minus 1. And so then if I have psi bar lambda dot v psi, that can be an invariant if I take, so psi goes to u psi if lambda dot v turns into u lambda dot v u dagger. Okay, so then this is an invariant. Lambda dot v prime is u lambda dot v u dagger. Sums over those. And then you can write out the individual components, because if I take then the trace, let's take the trace lambda I lambda dot v prime, that by our trace rule up there is 2v I. It's then on the other side, it's trace of u, so I need my lambda I there, u lambda I u lambda j u dagger vj. I've just pulled out the lambda dot v, the summation there. And this one was v prime. So v prime I is some rij, vj, with this being 1/2 trace lambda I u lambda j u dagger. So again, it just rotates these things among themselves in some way, which there's the rotation. Again, you don't need to know it in detail, but that's what it is. But you do need to know that if you want to form an invariant under of these guys, so let's take lambda dot v lambda dot v, so these are two of them. Okay, let me take the trace on that. That's then 2v I vi, so it's just taking the sum of them. That's an invariant, because if I make that transformation, it goes to trace u lambda dot v u dagger u lambda dot v u dagger. The u's all cancel out by properties of traces. Okay. And I have an invariant. So without knowing a whole lot about these matrices, knowing what they are, we know how to form invariants. We have invariants among the vector fields, among the interactions of the vector fields to the other fields. And the names of these go as the generic name. Psi is the fundamental representation. so of SUN. So it's n components, and VI is the adjoint. Okay, so one's n dimensional, the other is n squared minus 1 dimensional. Okay, so you can do this for any n and take n to infinity if you want. Okay, that's my group theory. Any questions about the group theory before I do Yang-Mills? Okay, so if not, let's do SUN gauge theory. Okay, so we did U1, so here's the reminder on U1. U1 we took psi goes to psi prime, which is e to the I alpha 0 psi. And that's a phase change, it's a unitary phase change. And we had this field, the photon field, which went to A prime, which was A mu minus 1 over E of the charge, d mu alpha, so the gauge change. Okay, so we want to mimic that. So here, if we're doing SUN, we're going to take psi goes to psi prime, which is U psi, where that's an SUN matrix. And then we have to have some gauge transformation, that gauge field that makes this invariant. Okay. But actually, the thing I forgot to say is that this alpha is a function of x. Okay, so here, to make this a gauge theory, we're going to take U is e to the minus I alpha of x dot lambda. And if you'll excuse me, I'm going to stick divided by 2. Clearly, that's the same thing, but it just makes the notation look better later on. It gets rid of some of these factors of 2. Okay, so the basic point is that this is going to be a function of x. Okay. So, what's the principle? Well, the principle is that, well, we still have psi bar psi as an invariant, but psi bar d mu psi is not. So if I want to, let's do it fermions, psi bar del slash is not. So we need to build a way to make that invariant, and we did that before by doing gauge covariant derivatives. So here let's try to do the same thing. I'm going to try to define a d mu covariant derivative, so gauge covariant derivative, such that d mu goes to d mu prime, which is u d mu u dagger. Okay, that's going to be the defining property, and I'll construct it so that it works. Okay. If then if I have psi bar id slash psi, where that's the covariant derivative, that turns then into, psi bar turns into u dagger. This turns into u d slash u dagger and psi u. So those transforms that way, which is then invariant. Here's psi bar I d slash psi, so it's invariant. Okay. So if that's that's my goal, that's my, okay. So sheesh. All right, let's try the following. Yes. Let's open up again. All right, now it's better. Okay, so let's construct it. Okay, well, just like before, we're going to have it involve, the d mu is going to involve the derivative operator. Of course, that's what it has to. And then I'm going to add a new piece, which is in g over 2 lambda dot a mu, where this is going to be the new gauge field. So AI with I is equal to 1 up to n squared minus 1. Okay. Okay. So d prime e prime u is d mu plus, I missed an I, sorry. There was I just stuck an I in there if you weren't looking. It's an I there, and g over 2 lambda dot a mu prime. We want this to be equal to u d mu plus ig lambda dot a over 2 u dagger. Okay, well, let's work out then what a prime has to be. So the derivative could act on something that sits off to the side there, just like this one, in which case the u and the u dagger annihilate each other. So that's the first piece works where the derivative acts on something else. If the derivative acts on the u, then I get something non-zero. So let's just, so yeah, the first piece was d mu, so there's no thing there. Then there's a piece which is plus u d mu u dagger. Okay, so I put it there so that it's acting on the u dagger. And then the other piece is plus ig over 2 lambda dot a, and I have a u and a u dagger on those, on the sides of that. Yes.
A is still four vectors.
Yes, A is a 4 vector, so I need my little u's, mu's there. I have most places. All right, there we go.
And also do not have the not product between lambda and a.
Yeah, so lambda dot a, when I write that symbol there, it's lambda I ai, and we sum over those, so the summation convention is there. Okay, so in SU2, these are the Pauli matrices, so maybe it's best to think of those, but this works for anything. So the this would then have three components and be tau, the Pauli matrices dotted into lambda, dotted into A. Okay, so tau 1, tau 2, and tau 3. Okay. But here they go over all of them. Okay. Well, actually here you sort of see the two features here. This one, if I forgot that preset, looks just like the transformation that I've been doing now to form invariants. This is some field that, like my vector field that I had up above, transforms to A prime is lambda dot A prime is U lambda dot A U dagger. That's the transformation that I did above. This is the gauge transformation piece. Here's the derivative of that. And so the net transformation is lambda dot A prime U, I'll put it over 2, is equal to U lambda dot A U dagger plus 1 over G. Actually, let's see. What do I need? I have, it's minus I over G. I'm getting rid of my factors of I also. Minus I over G U d mu U dagger. And there's an over 2 there. Okay. And you can then pick, again, so there's the matrix form of this. This is a traceless submission. It's not completely clear to you that this is traceless submission, but it is. If I expand this out to first order, you can see that it's going to be at first order, because this is just brings down U has a lambda dot alpha in it, and so this is a derivative of alpha. Actually, I'll write out what that is in linear order soon. But here's how you can project out if you want. You want the lambda A prime I is then just trace of lambda I lambda dot A prime over 2 is then this Rij, which I defined before, a J mu minus I over G trace lambda I U d mu U dagger. Okay. So this is the sort of rotation invariance. So these fields rotate among themselves. The second piece is the gauge change. And if I do this infinitesimally, first, actually let's say I have the answer infinitesimally. For small, if I want it for small alpha, it's here. I'm not going to work at A prime is AI minus 1 over G d mu alpha I, and then the rotation piece turns into F of ij k A K mu alpha j. Okay, again, so think of this in SU2, this is an epsilon tensor, so this is like a cross product, so this is the usual rotation piece in regular space, but this is an n-dimensional space. Okay, and I have proofs about how various things are Hermitian like they should be, but I guess I don't think I'll go through that. Okay, so here's our generalized gauge transformation. Whichever version of these you prefer. You can do this one, which is explicit, this one, which is the matrix representation. And so we've now made an invariant. So in a sense, we now know how to construct at least the fermion piece of the Lagrangian. We've got psi bar I d slash psi, with that d is invariant. Okay. The piece that's still missing is not only we have to do that, we have to do a kinetic energy piece for the gauge fields. So what we had before was minus a quarter F mu nu, F mu nu. This is in U1. Goes to what? Okay, so our next task is constructing the answer, which is minus a quarter F mu nu I, F I mu nu. That's the form, but we have to find out what F I mu nu equals what. Okay, so what's a good construction of that? Here's a very cute and clever construction of that. Let's take the following. I take covariant derivative of mu and commute it with covariant derivative nu. Okay. At this stage, we don't know what that is, but we know it's an invariant. Okay. And the way you know it's an invariant is because this goes to u d mu u dagger u. Actually, it's not an invariant. It has a particular form. U d nu u dagger, which transforms then like u d mu d nu u dagger. So it has this definite transformation property, and I could, if I wanted to, well, I can make invariants using that just by this trick. The key point is we're just about to calculate it. D mu commuted with d nu is going to be something that goes like lambda dot F mu nu, and in the normalization I'm choosing is Ig over 2. Okay, so we don't know what F is here, and even what it means, but we would then know that lambda F prime I mu nu equals mu u lambda F mu nu daggered. So there's a summation up there. So we have that transformation property, and it's then easy to construct an invariant using our tricks. Okay, so to calculate it is pretty easy too. This is it's d mu plus I g over 2 lambda I A mu commuted with d mu plus I g lambda I a nu over 2. And let me put a different index here, lambda j, lambda j. Okay, I need my index there. Okay, well, derivatives commute, so that does, the derivatives by themselves don't play any role. But there's a piece where this derivative acts on A, and then there's in the opposite order, there's this derivative acting on that A. That doesn't commute. And then the two A's don't commute either, because they're like the Pauli matrices don't commute. So the pieces that we pick up there are, well, there's the IG over 2, lambda, lambda I d mu a nu minus d nu a mu. Anyone see my mistake on the previous writing thing? I have a mistake right here. That should be a nu. So let's get it back to being a nu. There we go. Well, that's not a good nu. Let's make it nicer. There we go. Okay, so you have these pieces from the derivatives acting, and then the second piece is IG over 2 squared lambda dot a mu, let's make it lambda I a mu I commuted with lambda j a nu j. Okay. Well, this is lambda I commuted with lambda j. So this is that's a typical commutator is 2I f I j k lambda k and the a mu a j nu carries down there. Okay, so you see all the terms are proportional to a lambda matrix, a single lambda matrix. Either this one right here or this one here from the commutator. So it does have this form, lambda times something. And we can read out what something is then. If I do my algebra, then f I mu nu is d mu a I nu minus d nu a I mu is the minus g f I j k a j a k mu nu. Okay. So that's going to be our f. I'll make the invariant in just a second, but that's the f. Okay. So it has the usual piece like the photon piece, but it also has a piece with the interaction in it. And so there's these then describe self-interacting gauge fields, the gauge fields that carry their own charges. And then the final invariant then is if I take trace of lambda dot lambda I f I mu nu lambda J F J mu nu. Yeah, one should be upper to make it Lorentz invariant. That's going to be an invariant because it transforms like trace u lambda I f I mu nu u dagger. That's how the first one transforms, and the second transforms like u lambda j f j mu nu u dagger. These guys all disappear because of the properties of the trace, and so that's invariant. So it's an invariant. And we can write out exactly what it is by the properties of this. That turns into 2 fi mu nu fi mu nu by trace lambda I lambda j is 2 delta ij. You get that. So now we have our Yang-Mills Lagrangian. That's gauge invariant. So then overall the Lagrangian is minus a quarter fi mu nu fi mu nu plus psi bar I d slash minus m psi. So that's the Lagrangian that has an SU n gauge invariance. Okay. The content of that, let's quickly do content. Okay. So we have psi is psi 1 up to psi n. So there's n fields. We have, with some label, we have ai mu with n squared minus 1 fields. The interactions come, there's an interaction that sits right in the covariant derivative. The Feynman rule for that is minus I g over 2 lambda I, so this carries index I, mu, gamma mu. So instead of just minus IE gamma mu, there's now a color factor there. And up there, there's also Feynman rules. Oh, actually, I don't quite have them all written out. Let's quickly figure out what they are. There's, well, I know what they are in pictures. There's a piece there that has, since f has the derivative pieces and a derivatives plus a quadratic piece, when you square that, there's, in the square, there's these two and that one, so it involves 3 fields, and there's this one squared, which involves 4 fields. The 3 fields one then looks like minus IG Fij K, and just to be safe, I won't label things so that I can't be wrong, plus permutations. Okay, so there's something that looks like that. It involves one derivative one Fijk symbol, derivatives turn into momentums, and I've got it right up, except I haven't labeled it, so I can't, I haven't told you which one is P1, which is P2 mu, and just the counting factor. You can look this up in our book, for example. And then the last one, there's a quartic one, like lambda phi to the fourth, except it's more complicated here. This has no derivatives. This is of order g squared. It's minus g squared Fijk FLMK. So there's four symbols, IJK, and there's some G mu nu, G lambda sigma, plus perms. And I won't write out what lambdas and sigmas are. You can look. So let's say that's there. IJLM. There we go. That's K. K is summed over. So there's four free indices here, and I guess I've chosen to call them I, J, L, and M. Okay, so Yang-Mills has these contents, and so here's okay. So in doing this, typical the two applications that one has is one is QCD, in which case n is equal to 3. Psi is psi 1, psi 2, psi 3, psi red, white, and blue, or whatever your favorite national colors are. Red, white, and blue is not a good choice. But for n equals to 3, those are the different colors. And I runs from 1 up to 8, are the 8 gluons. And so that's all I'm going to say about QCD. And then the other application is the weak interactions. Here, n is equal to 2, so it's SU2. The psi are doublets, up quark, down quark sit in a doublet, neutrino electrons sit in a doublet, charm, strange, etc. ... They're doublets where the upper and lower ones are fields that we see having a different electric charge by 1 unit. The lower one is down by 1 electric charge from the upper one. And here the gauge bosons, there are 3 of them, AI. I equals 1, 2, 3, and A1 plus I2 or minus I2 turn into W plus and minus, the charge gauge bosons. A3 goes almost to the neutral gauge boson, Z0. And really, it's SU2 cross U1. U1 gauge boson has a B mu instead of, let's just call it B mu. And so it's the A3 and B mu turn into, they mix, and there's components of the Z0 and the photon. So it's a little bit more complicated. Again, that's not all I'm going to say about that, so that's not too much, but that's what it is. But there's the construction. So it's basically modeled after QED, but with a little relatively simple group theory thrown in. Yes?
So the photon is U1, the ENM is U1?
Yeah, so the photon is U1. And basically what it is, in this mixture here, there's a U1 here, but that's not exactly the photon. If you look at the couplings in the standard model of this, it's not the photon couplings. But after the Higgs mechanism works, you take a portion of this and a portion of that, you mix them in just the right way, and out comes the photon with its usual couplings, and the Z0 with some well-defined couplings. Okay? So there's a little technology getting from here to here, and that's the Higgs mechanism in the standard model, which is lovely stuff, but not on my agenda today. Okay? But so there are these two neutral ones, the neutral one from here, the third component one, and the neutral one from there. And that's, those are the and the leftover one is the U1 of E and M. Okay? So that's how you call the group theory stuff. Okay. Questions about that? Anything else? No. I'm going to stop the gauge theory stuff there, because I really